Good afternoon. So in this session, that is second session, we are going to learn about the neural network architecture. In the previous session, we have come to know about some overview of the neurons and the neural network. So here we will learn about the various types of learning schemes and the neural network architecture. Now the contents of this session are, we will learn about single input neuron, multiple input neuron, single layer network, multiple layer network, network architecture, network structure, recurrent network, about the learning schemes. Now the single input neuron, right? In the single input neuron, we have learned that what is the scalar input, that is your, we are representing as P, this is your scalar input. The scalar weight, that is your W, this is your scalar weight. This is your bias B. This is your net input, that means after W into P plus B, that will be the net input, that is your N. After N, we are getting the activation function, and finally we are getting the output. Now, if we can represent or connect with the synapse and the dendrites, we are saying this P and 1, these are my dendrites. This W is my synapse, or it represents the synapses gaps. This is your cell, this is your final cell or soma. The output is your axon. Now the schematic diagram is this, that is your P into W, B into 1. It is coming to the function f, and after that the output A is coming. Now what is the mathematical function? Mathematical function, it is saying that n equal to W into P plus B, right? That means n is equal to, that is your output is equal to W into P plus B. B is your bias. A is equal to, that is a function of n, right? What is the function of n? This is your A. N is equal to again WP plus B, that means we are getting A is equal to f of WP plus B. Now for example, we are taking W is equal to 3, P neuron values input is equal to 2, and bias equal to minus 1.5. So what will be n? N is equal to W into P minus, that is minus 1.5, that is minus 1.5, that is equal to 4.5. And A is equal to F 4.5, that means function of 4.5. That means if the function is your binary function, we have learnt about that if it is a binary, that means if xj is greater than 0, then automatically the output will be equal to 1. And if it is xj is less than 0, then output is 0. Or in bipolar case, we have learned that if xj is greater than 0, then the output is equal to 1, and it will be minus 1 if xj is less than 0. So these are the two inputs we have learned. So if it is your 4.5 and we are using the bipolar function, that means A is equal to will be 1. And if it is a binary function, then also it will be is equal to 1, because that 4.5 is greater than 0. Just like this we calculate for the single input neuron. Now similar case, if we bias and weight, that we know that the bias B is only like the weight W only. Biases are values that are added to the sums that calculated at each node. I have told you about the bias and weight. What do you mean by the transfer function that is equal to f? I have told about this is your f. F is the function. Now I have told this function is your, there are various types of function as I have mentioned in the earlier class also. But with the help of the MATLAB function also, we can use this transfer function for the implementation purposes. So there are three types of function we are using. One is your hard limit function, that is between 0 and 1, linear limit transfer function, and another is your sigmoidal function, right? Now what is the MATLAB command of the hard limited function? For the hard limited, we are writing HARDLIM. This is your hard lim. That is your hard limit transfer function. So how we can use it? For example, here I am writing one example, that is if n equal to -5 to +5, n equal to -5 to +5 with a step size equal to 0.1. So that is equal to your n. If n is equal to like this, and if we write a is equal to hard lim of n, if I write hard lim of n, right, we will get this type of signal. That means -5 to +5. If it is, that means 0, that means up to 0 it will be 0, and from 0 onwards it will be 1. We will get the just like as your step size signal. So this is for MATLAB function we use the hard lim. You can use for your in your laboratory, that you can just search. You can see that this how this hard lim function gives the output. So this is the function of this output of the hard lim function. Similarly, the linear transfer function. Linear transfer function we use the pure lin. That means purely linear. We use the PURELIN, pure lin. Right? So you have the input or the net, that is your WP plus B, and this will be the only will be on matrix. Now, for example, n is equal to this thing. If you are rating that a is equal to this, and if you are plotting this, we will get this type of signal, that is your linear function. Right? This we have written already in the MATLAB program. This is the inbuilt function of the MATLAB, pure lin. Third one, that is a log sigmoidal transfer function. So for the sigmoidal, as I have told you earlier also, this is the graph we get the sigmoidal function. So we write log SIG, that is your LOG-SIG. This is known as your log sigmoid function. So this is equal to 1 by 1 plus exponential e to the power minus x. I have written previously also, this is your sigmoidal function e to the power minus x. You can take x or you can take n. Here I have shown with n, that is your n equal to -5 to +5. Then if we get a is equal to log sig of n, and then if you get the plotting, then you will get this type of graph, that is your sigmoidal function, or you can write on your own the program, right? That was for the single input. I'm telling till now I am telling about the single input only. But if you have the multiple input matlab, for example, from P1 to PR, that is P1, P2, P3 dot PR, and similarly the weights are also associated, W11 to W1R. Then again the summation. So in the summation, what will be the n then? N will be equal to W11 into P1 plus W12 into P2 plus dot dot plus W1R into PR plus bias, that is your P. So that in matrix form we can write WP plus B. And output A is equal to again the same, that is your function of WP plus B. That means finally, if it is a single neuron or it is a multiple input neuron, the case is same. You have to do the summation, then you have to do the function. So this is your actually the, just 1 minute. I'm showing you again because we have marked on it, so it may not be so clear. Okay, so this is actually your multiple input neuron structure. Here I am showing this. This was your P1 to Pn, and this type of connection we give to the neurons. That means it will be like this. For example, there are various types of neurons. For example, these are my neurons, and these are my inputs, right? And finally you are getting the output. So each and every neuron, there will be the input will be going to each and every neuron, right? From this, here also we'll get the input, and similarly to the other side. This is known as your mesh network, that you will get the connectivity from each and every neuron to the other neurons. So this is your output, and this is your neuron only 1, 2, 3 and 4. For example, these are my 4 outputs. Right here I have not shown any hidden layer. This is only the 2 layers, only the input layer, and this is your output layer. So these are the connections I have shown, that what is the output, that is your from each and every neurons N1, N2 and NL, these are the outputs. And for example, if when we will do the action function, activation function, we'll get the outputs. So after single neuron, we get the single layer network. First of all, we have learned the single neuron and the multiple neuron. Now we will learn the single layer and the multiple layer. In the single layer, only the input layer and the output layer is present, right? And the weight matrix, this you know, the number of inputs and number of neurons and the how many number of inputs and all these things, you know everything. Now the weight matrix, it has been written like this. The weight matrix is represented as W11, W12 and W1R. Similarly, W21, W22, W2R for each neuron, for to each output layer neuron, right? So this is the weight matrix. I'm definitely sure that you must have understood that weight matrix. This is basically, for example, if there are 2, 3 neurons, 3 input and for example 3 outputs. Now if we connect, so this is your W11 and this is your W21, this is your W31, or otherwise we can write this is your W12, this is your W13, like this. So everywhere we will get the weight matrix W11, W12, W13, similarly W21, W22, W23 and W31, W32 and W33. That depends on the how many inputs are there and how many output neurons are present. This is about the multiple layer network. In the multiple layer network, what happens? There are input layer also, hidden layer also, and the output layer also. So whatever output is coming from the input layer, it will be input to the hidden layers, and whatever output we are getting from the hidden layer, that will be input to the outer layer, and finally the output will be coming in terms of A. You have seen that here also we have given that is your function of W11P and I, then is equal to A. This is actually, first of all, the input were P. So that's why I have given here the matrix P. After that, the input will be this at matrix A1, right? This one, the matrix A11, A12 and A1L. So we have given the input as A1 only. After that, A2, A21, A22 and A2. Then similarly we are getting the input as A2. That means the output of the input layer will be input to the hidden layer output will be the input to the output layer, and finally the output will be coming. So the next is your network architecture. Now in the network architecture we have some points. We have neurons, we have the interconnections, we have the network topology, and we have, it can be positive. I have told you positive means excitatory, negative means inhibitory, absent means 0, and the information is stored in the connection weights. Now network structure. In the network structure we have the input layer, we have the output layer, we have the hidden layers, and there may be from 0 to several hidden layers in a network, but of course definitely that you have to choose that what type of hidden layer and how many hidden layers are required depending on the trial and error method, right? Now depending on the interconnections of the the layers, we can select as it is a feed-forward network or feedback network or the recurrent network. In the feed-forward network, I have told that is when no node output is an input to a node in the same layer or the preceding layer. That means in the feed-forward layer, there cannot be anything. For example, there are this type of network, but no output is going to input to the any layer. That is not the case of the feed forward layer. In feed forward, there should not be any feedback network, or it means to say that no output will be the input to the same layer or its previous layer, right? So this is not the this is the feed forward layer, that is, there should not be any connections of the feedback. But if there are connections of the feedback, then it is known as your feedback network. That means if any single, at least one single connection can be like this. So that is your feedback network. Feedback network that have the closed loop is known as your recurrent network. What do you mean by saying that? Let us see. So this is one recurrent network example. What is recurrent network? You must have learnt about the recurrence in case of when you are calculating in a program factorial. That time we say that that problem is your recurrence problem. That means factorial, when you calculate the output, again you give the input to an next cycle. The output of the one cycle, again you give input to the second cycle, or the output of the previous one, you give input to the next one. For example, if you want to calculate factorial 7, you give n equal to 7, then after that n is equal to 6, after that n is equal to 5, and correspondingly you get up to 0, and finally you get the values of factorial 7. Right? So this is actually basically recurrence formula. So in case of recurrent network also, what we do that, for example, here you just see, finally, initially we have done A0 equal to P. That means P is your initial neuron, that is your P, and it is your A0. A0 means this is your initial condition A0. Finally, A1, A is your output, right? So first of all, when we'll start the implementing that network, we say that whatever initial condition P is there, that will be instantly, that will be my output. And next output will be that A0 will be as an input to the W. That means this A0, what we are saying, that W into P plus B, that was our condition. Now in this case, P is your A0. So we are inputting A0 into W, after that plus B, and both of this, the output will be calculated as setlins. Setlins is your the final output with the help of some function. That means you can give the sigmoidal function, you can give any function. The setlins is also a function. So you are getting A1. And this A1, again you are inputting, again you are getting A2. And similarly, A2 you are giving the input here with this, and similarly this is actually feedback, and similarly you are getting the A3. And finally the common solution will be that AT into W plus B, and after that some function, with some function, that can be any function, that we are getting, and finally we are giving the T plus 1. So how to get AT? Here we have given the delay part. This delay part is this. Delay is basically, there are two parts. One is your delay block, another is your integrator block. Delay block is your, for example, if you are giving the UT as an input, and if you are giving the delay, the AT will be UT minus 1. That means 1 delay. Similarly, in integrator, what you are getting positive 1. That means you are getting the integration, addition, right? So in case of the recurrent network, we are getting the delay part. That means we are getting AT plus 1, then delay, then AT. Again, you are giving the input. So this is known as your recurrent layer network. That means there are three types of network. One is your feed forward, another is your feedback, any of the single network. And if you get the closed loop, that means it will be continuing again and again, again and again. It will be going. Recurrent problem is there. Then it will be known as your recurrent network, where the input, the output will be dependent on the previous output, right? Output at any time, at any time, output will be dependent on your previous output. That is known as your recurrent network. These are the types of the network. Now coming to important parts, that is your learning schemes. There are two types of learning used in neural network. One is your parameter learning that I have given here, that is known as your parameter learning. Another is your structure learning. In case of parameter learning means we are learning the weights. We are learning the updation of the weights and biases. That is known as your parameter learning. If we do the structure learning is basically the learning of the number of nodes and the connection types. That means how many number of layers, how many number of nodes, how many types of the connection, what are the types of the connection you are giving, what are the types of learning you are giving. That is known as your structure learning. There are two types of learning. One is your parameter learning and another is your structure learning. So these kinds, each kind of learning can be divided into mainly three parts. One is your supervised learning, another is your unsupervised learning, and third one is your reinforcement learning. That was your three types categories. One is your supervised, another is your unsupervised, another is your reinforcement learning. These three are the types of the learning schemes, right? So let us go one by one. Supervised learning. With the name only we can understand there will be the supervisor in this learning. There will be the supervisor in this learning. Right? Supervised learning means there will be the teacher. You have the teacher or the supervisor who will say that your desired output was this, but you have got this, right? So depending on the data, you can just update your weights. So here only we are showing this is your input from the environment. You are getting the inputs and it is going to the learning system. Teacher is giving that what is the desired response. That means you have your targets. You have your targets and you have the actual, you are calculating the actual response, and both of these two you are calculating the error or some comparison you are doing, actual response and the desired response. Finally you are getting the error signal and again you are learning the system. That means depending on the error you are saying that weight should be updated positively or negatively, or weight should be increased or weight should be decreased. Like this, again the actual response is there, again the desired response is there, then again the error is you are calculating, that finally the error signal is going to the learning system and again you are getting the actual response. Like this you will learn with the help of the supervisor, right? In case of the reinforcement, this is similar as your supervisor only, but it will not give you the target values. It will tell you your result is right or your result is wrong. That means it will give the critics. Critics, you know, that we are giving critics. That means we can give only the suggestions, whether it is wrong, whether it is right. But you are not giving the actual response that your target should be your 0.1 or your target should be your minus 0.3. You are not giving that. But the teacher is giving, supervisor only, but teacher is giving only the output that your result is wrong, your result is right. Depending on this, you have to check that how to go about it, depending on the output, depending on the, you know, the previous prior knowledge of the system, anything. With anything you have to just learn your system. So this is the part of the supervisor learning, that is your reinforcement learning. What type of learning? That is, learning will be done and the actions will be taken, and finally again that the critics will be given by the system, and again the depending on the critics we will do the learning system. In case of unsupervised, in case of unsupervised learning, what we get, that we don't have any teacher, we don't have any supervisor. Depending on the value output, we have to decide ourselves and we have to learn the system. This is known as your unsupervised learning. That means there will be no supervisor to tell you whether your target is right or target response is right or response is wrong. Just seeing the outer response or seeing the diagram or seeing the image or seeing something visual something report, you have to declare that your response is right or your response is wrong. Similarly, you have to learn the system adaptively. You have to learn the system. This is known as your unsupervised learning. Now, due to this learning schemes, these are the learning schemes, we have some learning rule also. First rule is your Hebb's rule. Hebbian learning बोलते हैं इसको. Hebb's rule. Hebb's rule had been developed in 1949. It is an unsupervised learning, right? He has given some rule that how weights will be updated. How weights will be updated, but no target value is present. But he has given some rule. With this rule, you can update your weights. What it is saying, it is saying that learning signal is the output of the neuron. That means only if you get the output, that is your Y as the output, your weight is dependent only on the output. How? It is with the correlation effect, that is your X into Y transpose. He has given the rule. We have to go with this rule. That means its rule says the new weight W is equal to the summation of all the neurons and your X, your neuron input, and whatever you have given the output. That should be transpose, right? Transpose is basically for the rows and columns matching, because multiplication, in multiplication we have to take care of that the number of rows should be, the same as your number of columns. For this, the transpose has been done, but it is a correlative weight adjustment. So it has told the Hebbians, we will do in details Hebbian learning in MATLAB programming. When we will do this Hebbian learning again with the example and weight. So Hebb's says that this is the rule. I have given the rule that how the weight should be updated. So each time weight, first time you have taken the random weight. After that you have find out some Y, and the new weight will be X into YT. Again you calculate Y with these weights. Again you calculate the weight. Like this it will go on based on the weight adjustment, and finally the desired output you will get. I will give you that how the desired output will be checked. Next is your perception learning tool. That we will take the session tomorrow about the perception. This is your one topic basically. Their learning signal is equal to desired signal minus the actual response. It says that if desired signal is greater than the actual response, then you adjust your weight like this. Some rule is there. And if it is desired signal is less than the actual response, then your adjustment will do like this. And if it is same, then you don't do any adjustment. Like this, it has given some rule, that is your Rosenblatt. He has given the perception rule, that is known as your Rosenblatt. Name I will just write, Rosenblatt. He has given the perception learning rule. He has told that if the desired signal is greater than the actual response, that means the desired signal, you can say that should be 1, but you are getting 0. That time weight should be decreased. That means it should be subtracted from which? From some value. Which value? That we will see in the rule. That is your alpha into xi. That is your learning rate into xi. That we will see in the next classes, right? Tomorrow's class we will see that what is the rule. And if your desired signal is 0, but actually you are getting 1, that means you are getting if your desired signal is 1 and actual response is 0, that means the weight should be increased. And if your desired signal is your 0 and actual is your 1, that means it should come as 0. That time weight should be decreased. And if your both are same, that means no adjustment is there. That means WT plus 1 will be as it is your WT. That means that time at time t is equal to 1, what was your weight, that should be same as your previous time. So that is your supervised learning. Here the perceptron learning is the supervised learning, because every time you are getting the desired signal and you are getting the minus, then you are getting the error signal, and accordingly you are doing the improvement in your weights. So this is your supervised learning. Delta learning tool. In delta learning tool, we are giving the concept of the derivative. I will tell you today only delta learning tool. After we complete the learning schemes or the Mac-Kulak-Pitts model, then I will tell about that what is delta learning tool. Delta learning tool is also the supervised learning. It says learning tool is equal to error signal into derivative of activation function. That it is telling. Derivative of activation function means if your I have told you function is your f, right? That means learning tool says that learning rule equal to, it will depend on the derivative of the function, that is your f dash. Right, whatever activation function is there, it will be dependent on the derivative of the activation function into the error signal. So that should be your learning rule. That I have shown here, that is equal to f net if it is your activation function. Here I have written this is your f net, or this is your f dash net. That means it is the derivative of your activation function and your error signal, that is your d minus o, that is your desired minus actual output response. Then it will go to the multiplier, that is your multiplication, error signal into derivative of this. Finally you are getting the learning tool, and accordingly the weights will be updated. Accordingly the weights will be updated according to that rule. So this is your delta learning tool. Another learning tool is your competitive learning tool. It says that those neurons which respond strongly to input stimuli have their weights updated. That means if there are 4 neurons, and with these 4 neurons, the highest weighted neuron will win the system, and the weights will be updated according to that neuron. That means if your weight is, there are 4 neurons, your weight is -1, -2, 1 and 2. That means the weight 2 with which 4th neuron is connected, it will be the winning neuron, and according to that neuron only the final weight will be adjusted. That is known as a competitive learning. That is, all the neurons will be in the competition, and the winner will taken care of, and according to the winner weight, the final weight will be adjusted for all. Again the weight adjustment will be for all, not only for the 4th neuron. Weight adjustment when we will do for all the neurons. Again the winner neuron will take over. Again the weight adjustment will be done according to the winning neuron. So today we will tell about the Mac-Kulak-Pitts neuron model. Mac-Kulak states that Warren Mac-Kulak and Walter Pitts, both of them had created this model in 1943. Right? Both of them had created this model, that is known as your Mac-Kulak-Pitts neuron model. It says there are M inputs, that is your L1 to Lm. This is your inputs. This is your L1. This may not be so much clear, but I am just telling you, this is your L1, this is your L1, this is your L2, and similarly this is your Lm. There are M inputs and 1 output Y. This is your output. Here we are getting W1, W2, W3, and similarly Wm. These are my weights. This will be multiplied, this will be summation. Here I have kept the threshold T, right? If the sum is greater than equals to T, then the output will be 1. If the summation is less than T, then the output will be 0. T is our real value, what we want as threshold, right? That will be taken care of by us, that what will be the threshold. The linear threshold gate simply classifies the set of inputs into two different classes. One is your 1, another is your 0. Either it will be 1 or it will be 0. So this says the McCulloch-Pitts neuron model. Now let us solve one example of AND function. Now I have to go to the board. Now AND function. AND function says this is your truth table of AND function. These are the two inputs, that was your x1 and x2. This is your output. This is 0, 0, 0 output, 0, 1, 0 output, 1, 0, 0 output, 1, 1, 1 output. So this is my desired response, right? This is my desired response. That means I should get, this is my target. That is, if you AND these two values, we should get 0. If we AND these two values, we should get 0. Now I will show you that with this help of this McCulloch-Pitts model, how I can show that my actual response should be same as your desired response if we take the weights like this, right? Now if we just take a graph of this values, if we get the 0 and 0, for example, this is my x1, this is my x2. If we get 0 and 0, that means we are getting the 0 value. If we get 0 and 1, 0 and 1, we will get 0 value. If we take 1 and 0, 0 and 1, then also we will get 0 value. 1 and 0 means this is your 1 and 0, and this will be 1 and 1, we will get the 1. That means we will give the solid value, right? Solid field 1 as 1 and the other values are 0. We will get in the space, this is known as your linear space or the hyperplane space. So we are getting this type of value. So if we want to separate, because we are getting two classes, either it will be 1 or it will be 0. Now if we want to separate these two classes, we can draw this line which will separate this into two planes. One, it will be one side, and another 3, that is 0, will be in the other side, right? Now if we just represent this graph into the signals or the equation, what we will get? We will get, for example, something should be, that should be your boundary equations that I have shown here. That output will be the signum function. Signum function is your, that is your, this is your SGN, that is your signum function, that is your hard limit function. Hard limit function is also known as your signum function. So the W1 into IN1 or X1 you can take, W2 into IN2 and minus theta. Theta is your threshold. I have taken theta as your threshold. So the function will be, that is your, we are getting what we are getting, the out equal to signum function of the x1 into W1 plus x2 into W2 minus theta. Right? This is our function. Now if we calculate like this, I have calculated here. For example, you see this is your boundary equations. That means you will get equal to 0. If you want to find a linear equation, we have to give the equal to 0. So this is known as your boundary condition. So boundary condition will be W1 into IN1 or X1, whatever you are taking, W2 into X2 or IN2, whatever you are taking, and minus theta, that was your threshold, equal to 0. That should be my boundary conditions, through which this is my boundary conditions. Boundary conditions in the left side will be some classes, and the right side will be some other classes. These are the two classifications under this boundary condition. So this is equal to 0 is the boundary condition. And what we get through this IN2 from this equation, what we are getting IN2 we are getting, as I have told, written here, that is equal to W1 by W2 into IN1 plus theta by W2, that we are getting. And if you are comparing with some linear equations, we know linear equations function is your, the equation is your y is equal to mx plus c. You know that? The equation that I have written here, that will be mx plus c. M is your slope and c is your intercept. C is equal to intercept. In our case, in this case, what we have written, that is our boundary conditions. In this boundary conditions, the slope is equal to, what will be slope? M is equal to minus 1. M is equal to basically the minus 1. M is equal to minus 1 means what? Because it is the negative slope. And if you getting this type of equation, then we give that this is your M is equal to 1, right? Since we are getting then the negative slope, so we are getting, in this our case, the slope is equal to actually minus 1. Now if we consider this as a slope that is equal to minus 1, that means we are giving that W1 equal to W2 equal to 1. If you give W1 equal to W2 equal to 1, that time only we will get IN2 equal to minus IN1. That means minus 1 into IN1. That time only we will get the slope is equal to negative, that is your minus 1. So we are considering that W1 equal to W2 equal to 1. Now W2 equal to 1. Here also we are getting W2 equal to 1. Now what about the C? Now we are giving that if this is equal to C, that means we are writing, for example, again we are drawing, this was our case, this is 0, this is 1, this is 1 and 1, this is 0 and 1. This was my solid, right? Now to separate this, we are drawing some line. So this will be how much? By main only we can understand this will be 1 and this will be 0.5. So we are taking C equal to 1.5. C equal to 1.5. C equal to 1.5 means this theta equal to 1.5 because W2 equal to 1. So mx plus C. C equal to 1 means theta is also equal to 1.5. That means we are getting three values. One is your W1 equal to 1. W2 equal to 1 and theta is equal to plus 1.5. This three value we have got from this linear space. Now let us see really with this weight or this theta, should I get this desired output, that is 0, 0, 0, 1, or we are getting some other values? If we get the same, that means our neural network model is right. That means W1 is equal to 1, W2 is equal to 1 and theta is equal to 1.5. But if we get the wrong values, that means our assumption is wrong. Then again we have to take the new assumption, then we have to calculate, right? This says the McCulloch-Pitts model. Now let us see that again, that whatever we are getting, really we are getting this output or not. Now again we are writing one tabular form. Here we are giving the, for example, input 1. This we are giving the input 2. This is your 0, 0, 0, 1, 1, 0 and 1, 1. These are my 4 inputs. Now what equation we have? We have the W equal to W1. W1 equal to 1 we have taken. W2 equal to 1 we have taken. And theta is equal to 1.5 we have taken. Now, if we get the W1, W2 and is your theta, now you see that W1 into IN1 plus W2 into IN2. What we are getting? First case we are getting 0 only. Second case we are getting 1. Third case also we are getting 1. Fourth case we are getting 1 plus 1, that is your 2. Right? Next portion. Next portion is what? W1 IN1 plus W2 IN2 minus theta. That was our actual equation. W1 IN1 plus W2 into IN2 minus theta. Theta is your 1.5. Now here we are getting minus 1.5. Here we are getting minus 0.5. Here also we are getting minus 0.5. Here we are getting only plus 0.5. That is a positive 0.5. After that, the output is what? Signum function. Signum function of this one, W1 IN1 plus W2 IN2 minus theta. That means signum function of this is says if it is greater than 0, that means hard limit. If it is greater than 0, then we will be getting 1. If it is less than 0, then we will be getting 0. Now this is less than 0, that means signum function of y will be equal to 0. Here also we are getting y is equal to 0. Here also we are getting y is equal to 0. But in this case, we are getting signum function is equal to 1. That means we are getting as desired output. Desired output also should be like this. And with the help of the Mac-Coulomb-Pitts model also, we are getting this output, that is your 0, 0, 0, 1. Now similarly, we can find out for the, this is for the AND function. Similarly, we will get the OR function. Now let us tell about the OR function again. This is your OR function. In the OR function, what we are getting, the tabular form says the OR function is your, this is your IN1, this is your IN2, and this is your Y. 0, 0, then we are getting 0. 0, 1, we should get 1. 1, 0, we should get 1. 1, 1, we should get 1. This says the for the OR model. And OR model, when we see the space, we are getting 0, 0 as 0. That means here we are getting 0. 0, 1, we are getting 1 solid. 1, 0, also we are getting solid. That is 1. 1, 1, also we are getting solid. This is also 1. Now, if we do the boundary to classify this, both of them, that is one class will be 1, another class will be 0. Now, we have to straight boundary area is this. So, this is your boundary area, right? Where we are getting, again same thing we have to do, that is your minus W1 by W2 into IN1, IN2 equal to plus theta by W2, like this, just like as we have done it before. So here also we are taking, this also we are taking m is equal to only minus 1. That means that is slope is equal to minus 1. So slope is equal to minus 1, we are getting the W1 equal to W2 equal to 1, that we can take. And what will be theta nowadays? Theta will be, now it is only 0.5, right? That time it was here, that is your 1.5. Now we are saying if this is 1, this should be your 0.5. So theta we are taking as 0.5, right? Now let us see again the case if we take the W1 and W2 equal to 1 and the theta is equal to 0.5. Now let me draw this. That is your one marker. Just let us take one this. That will be x1, right, or the in 1. This will be input 1. This will be input 2, and finally W1 into input 1 plus W2 into input 2 minus theta, and finally we will get some output where the W1 and W2 in this case we are taking as 1 and theta we are taking as 0.5. So let us see what we are getting, 0, 1, 1, 0 and 1, 1, right? Here W1 is equal to 1, W2 that is 0, 0. Then is your minus 0.5 only we are getting. Here we are getting 1 minus 0.5, that is your 0.5. Here also we are getting 0.5. Here we are getting 2 minus 0.5, that is your 1.5. And if we get the signum function of this, we will get 0, 1, 1, 1. And this is our desired value, that is your, in case of OR function, we should get 0, 1, 1, 1. That means in this case, if we have taken W1 equal to 1, W2 equal to 1, that means 2 inputs, that will be 2 inputs and 2 weights, and finally that will be the signum function, and finally the output. The model is like this. The model will be like this only for the AND function and for the OR function. The model is like this. This is your input, that is your x1 or the IN1. This is your IN1. This is your IN2. This is your summation. Here we are giving the theta. This is in case of AND. In case of AND, we are getting that 1. This is also 1, and theta is equal to 1.5. Finally, we are giving the signum function, that is this. Signum function is this, and finally we are getting the output. In case of OR, this is your AND. In case of OR, nothing is there, only the theta will be 0.5. Then you will get the OR function. So this is your AND function and the OR function. Similarly, you can do with the help of NOT or with the help of the AND NOT function. Linear separable. I'm coming to this. So this is your AND function example, and similarly this you have to solve for the OR function that I have told, and you have to solve yourself for the NOT function. NOT function, you know that what is the NOT function? NOT function and the AND NOT function. This you have to do yourself. AND NOT function is your x1, x2 bar. X1, x2 bar means what? NOT function you know, that is your 0 for 1 and 1 for 0. The truth table is this. And for the x1, x2 bar, what is the truth table? I'm just giving you the truth table first. If it is 0, 0, then it will be 0. If it is 1, 0, then it will be 1. If it is 1, 1, then it will be 0. Sorry, it will be last. Then if it is 0, 1, then also it will be 0. Right? That means what? That means what truth table says, that only it will be true if your first value is 1 and the second value is 0. Only in that case only the output will be 1. Right? That means only for this case 1 and 0 the output will be 1. For the other 3 cases the output will be 0. So this is the truth table for AND NOT, and this is the truth table for NOT. And I will expect that you, all the remote center coordinators, you do this for you just check it that whether your participants can complete it or not, that you have to solve for the NOT function and the AND NOT function, right? So I'm sure that that will be understandable for you. And this function, whatever we have told, that which can be, you know, the separated linearly or with the outer boundary condition, that is known as your linear separability case. Linearly separable into the 2 classes, 1 and 0. Now let us take another example, that is your XOR case. The XOR case says that if it is 0, 0, I have telling that if it is the 0 and 0, then the output is 0. If it is 0, 1, then output is 1. If it is 1, 0, then also output is 1. If it is 1, 1, then output is 0. Right? So this is said by the XOR equations. Now if XOR we put into the linear space, we can see that this is for 0, this is for 0, and this is for 1, and this is for 1. And accordingly you can see that if the condition is like this and you cannot solve this with the help of only one boundary condition, it is not possible. Never it will be possible. Now what we can do, we can say that we can spread the 2 boundary conditions. Then only we can say that this one will be in one space and this, both of this will be into the another space. That way we can classify into this too. So we can solve this into various ways. There are 2 ways of solving this. Basically the XOR operation can be done, can be used, or can be written as like this. The XOR can be written as the XOR function. That is x1 XOR x2. It can be written as x1 x2 bar plus x2 x1 bar, right? Or in otherwise, it can be written as x1 plus x2 into x1 x2 bar. So you can write in both the ways. Either you can write it x1 x2 bar plus x2 x1 bar, or you can write x1 plus x2 dot x1 x2 bar. x1 x2 bar is your NAND gate. This one is your OR gate. Now we have told about AND gate, right? In AND gate, what we have found out? W1 is equal to 1, W2 equal to 1, and theta is equal to 1.5. Now, in case of NAND gate, when you will see that you should get the NAND gate will be optimized, or NAND gate will be implemented if you take W1 equal to -1, W2 equal to -1, and theta is equal to -1.5. Just a negative term from the AND gate that you will get. And OR also you have already got for the OR gate, W1 equal to 1, W2 equal to 1, and we have got theta is equal to 0.5. So we have got each and every operation. Now we can check that with this operation, that is your, first of all, we will do the OR, second we will do the NAND, and then we will do the AND, both of this. Then we should get the output of XOR with the help of this Mac-Coulomb-Pitts model. Now let us see one by one. First of all, let us see that what will be the OR. Now let us give again the truth table. Now first of all is your x1 and x2. That is your 0, 0, 0, 1, 1, 0, and 1, 1. XOR, in the XOR, what we are getting? That is, first of all, it is, since it is not possible within the one single boundary, we will do into the two steps. First of all, we will do the OR, and second one we will do the NAND, and then both the outputs will be doing the AND, and finally the output will come. Now the equation will be, the diagram will be, this was your x1, this is your x2. First of all, we will do the OR, right? First of all, we will do the OR operation. And in the OR operation, we know that the output or the weight should be 1 and 1, and the bias should be 0.5. So this is my bias, that is your 0.5. Next is your NAND. NAND, it is saying that x1 and x2, again, this is your NAND, for example, x1, x2 bar. We are telling that from x1, this input will come. From x2 also this input will come. But the weight, it is saying that it should be -1 and it should be also -1. And the bias should be -1.5, right? According to our condition. And finally, the output will go, and it will go to the AND operation. And in case of AND, we will get the W1 equal to 1, W2 also equal to 1, and finally the bias is equal to 1.5. And finally the output will be given. And we have to see that output will be the same as your output of the XOR. If we get the same output of XOR, then we will be confirmed that the circuit, whatever we have written, or the weights, whatever we have given, that is a correct weight implementation. Now let us see x1 and x2, and the OR operation is your 0.5. Matlab x1 into W1 plus x2 into W2 plus theta, that is your 0.5. This is, sorry, minus theta, that is your 0.5, right? Now what we are getting? 0, 0 and minus 0.5. That is your minus 0.5. Here we are getting 0.5. Here we are getting 0.5. And here we are getting 2 minus 0.5, that is your 1.5. So it is output is coming from the OR. That means we are getting what? We are getting 0, 1, 1, 1. That means here we are getting 0, 1, 1, and 1. And similarly for the NAND gates. Now again we are getting for the NAND gates, x1 and x2, 0, 0, 0 1, 1 0 and 1 1, and output we will be getting, again NAND gates will be getting 1 1 1 and 0. That means from the NAND gate we are getting 1 1 1 and 0. This is your from the NAND gates. Now this output will be taken to the AND gate with the weights, that is your 1 and 1, and is your bias 1.5, and finally the output we will calculate. Now here we will calculate x1 into W1, x1 into W1 plus x2 into W2 minus theta. Theta is equal to, we know that is 1.5. So let us see. This one, first one is your 0, then it will be 0. x2 into W2, that means 1 into 1 minus 1.5. That means it will be minus 0.5 only. So this will be minus 0.5. In this case, 1 into 1 plus 1 into 1, that is be 2. 2 minus 1.5, that will be positive, that is be 0.5. Again in this case, 1 and 1, that also will be positive, that also will be 0.5. And 1 and 0, 1 and 0 means 1 minus 1.5, that will be minus 0.5. So this will be your end, and what we are getting? We are getting the output, we are getting 0, 1, 1 and 0. This we are getting 0, 1, 1, 0. Now you see that what was your XOR output, right? XOR output was same, 0, 1, 1, 0. That means from when you are getting 0, 0, we are getting 0, and this is your 0. When we are getting the 0, 0, we are getting 0, 0, 1, we are getting 1, 1, 0, we are getting 1, and 1, 1, we are getting 0. The same output we are getting here. That means according to our case, whatever weights we have taken for the AND gate, for the NAND gate, for the OR gate, these are perfectly all right. And with the combination of these 3-4 gates, we can recognize the XOR gate. So XOR gate, since we cannot directly do the linearly separation, so this case is known as your non-linear separability case. Right? Non-linear separability case. Now, linear separability case, directly we can put the weights or the biases, but in non-linear separable case, we can take the combination of more than one and we can solve our problem. This is the basic solution of the gates, right? Or in other ways, you can do in the other way also, as I have told, that is x1, x2 bar, x2, x1 bar, and OR of z1 and z2. That also you can do, right? Because n naught, I have not told you, in the n naught case, we have the 1 and minus 1 as your weights, right? The W1 is equal to 1, W2 is equal to minus 1. When you will do, you will get to know. So in this case also we can do like this. That is x1. This is your x1, x2 bar. This portion is basically x1, x2 bar. That is your x1 n naught x2. This is your x2, x1 bar, and both of this OR. That means x1, x2 bar plus x2, x1 bar. This is also the logical error. So any one of these two methods you can do and you can solve your problem. So this is the actually basically the decision hyperplanes and the linear separability, what I have told you. If we have the two inputs, then the weights define a decision boundary. This is a one-dimensional straight line in the two-dimensional space. So this is your hyperspace and the one line. If we have the n inputs, the weights define a decision boundary that will be the n-1 dimensional hyperplane in the n-dimensional input space. That I have told. This one also we have done, the W1 into IN1, W2 into IN2 minus theta is equal to 0. So that was the for the two inputs. For the many inputs we can get the, this should be the decision boundary. This hyperplane is clearly still linear and can still only divide the space into two regions. We still need more complex transform, the XOR type that I have told you. Otherwise, XOR function also can be separated or can be recognized with the help of the Adaline network. This is known as your Adaline or Medalline network that we will do tomorrow. That is your Adaline. After perception, we will do that is your Adaline or Medalline. These are the Medalline network. These are the two networks, adaptive network. These are the two networks, multiple adaptive and adaptive learning method. These are the two networks with which also we can recognize the XOR operations. But this way also we can recognize. So with the McCulloch-Pitts model, we can recognize the gates, different types of gates. Now before that, just we will see about the delta learning method, because we have already done the other methods. We will do the Hebbian learning method and also, but delta learning method we have not done. So let me see about the what do you mean by the delta learning method. So as I have told you, the delta learning method basically takes care of the error signal. Now what it does, for example, in case of the delta learning, we have the del W, that is your del, then W. This is actually basically alpha into T minus Y in, that is your output, into Xi. So this is your the formula for your updation of the weights, right? Delta W is equal to alpha is your learning rate. This is known as your learning rate. That means how fast it will learn. If you give the learning rate alpha is equal to maximum value, for example 1 or 3 or 6, so it will be very fast and the result will not be accurate. But if you give the smaller value, for example alpha is equal to 0.1 and 0.2, then you will learn, the network will learn very slowly, but automatically the accuracy will be more, but time will be very more time consuming will be there. So that's why we have to choose the learning rate as a 0.9, so that we can get, this is the optimal value of the learning rate, so that we can get the optimal time also, and the accuracy also we can get fast. Now in case of delta learning rule, we calculate the error. So first of all, let us see that what do you mean by the error. Error is given as Tj, any type of value of j for 1 to n, Tj minus y in ij whole square. That is the error signal representation. That is your summation of, for the all signals, all neurons. For the jth neuron I have shown. So for all neurons it will be plus 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 Tj minus y in j. That means target value of jth neuron and the output of the jth neuron whole square. That is given by the error signal. That is given by the error signal. When we want to minimize the error signal, that means we have to do the derivative. Let us do the partial derivative of this. That means we can say that delta E divided by delta Wij. Let me write here only, because I suppose that it will not be visible because the marker is not so much, this thing. So let me do it here only. Let me introduce one slide and let me do it. Okay. Now let me write it here. Right. Now we are getting, finally we are giving that E is equal to, we are getting the summation of, I have told that Tj minus y in j whole square. So this is my error for all j, right? Now if we want to remove or if we want to reduce the error, we do the partial derivatives. So we do the delta E divided by the delta Wij. That means with case of the weights, because we have to update the weights. So what we can write, that is equal to delta Wij. Capital Ij means that all i's, all j's, but all input neurons, all output neurons, right? and it is the same E, you can just change it, that is your, in replace of E we can write ytj minus yin whole square. So that is your delta E by delta j, but only one term, if we just select for only one term, after that we will do the generalization. So let me tell about only the one term, that is your tj minus yin whole square. That is, let me calculate, this is not for all j, this will be for all j. Let me calculate for only one neuron, after that we will generalize for the all the neurons. So del wij tj minus yin is equal to whole square. So that will be your this thing, del E by del wij. Now del E by del again next calculation what we can do, that del E by del wij equal to, now we can do the partial derivative of this, that will be 2 into tj minus yin, right, 2 into tj minus yin, and this will be your minus 1, tj is your constant, and we can write that yin divided by del wij. That means the output by the del wij, and we are calculating the partial derivative of this, that is equal to minus 2 into tj minus yin into del yin divided by del wij, right, that we have taken. And let me write it here. Right, another options I'll be writing there. Now yin, finally what we are getting, that is your, here we are getting, that is del yin divided by del wij. Now del yin is what? Yin, it can be written as, that is your the output. Output is basically the summation of this input and the multiplication of the weights. So we can write yin is equal to summation of xi into wij for I is equal to 1 to n, right? Now what will be the del yin divided by del win? That will be basically the only the xi. So similar things we will do here, that minus 2 into tj minus yin, and del yin by del wij is basically the xi. So what we can write it here, that is delta wij equal to, we can write as your alpha tj minus yin into xi, capital Xi, that we are doing the into generalization, because here only we have taken only single j or single I, that we are taking the single small I, that is your xi. But when we will do the generalization, we can write that alpha into tj minus, alpha is what? Alpha is basically this minus 2 into this. So this is your alpha, that is your constant, minus 2, then tj minus yin, that we have got, and with this help of del win and del yin and del wij, we are getting as your xi. So this is your for the single output. Now if we get the multiple, several outputs, then we will get the this type of equation, that is del wij equal to alpha tj capital J minus yj into xi capital Xi and f dash. We will get the derivative, that is your f dash. So this only I have told in the previous classes, that delta learning is basically the error signal, that is, this is my error signal, this is a constant, error signal into the derivative of the activation function. So in case of delta learning, the basic model is your that error signal into the derivative of the activation function. How we get, I have shown just a method that how we can find out that in case of delta learning what should be their weight updation. For the Heavian learning, for the perceptron learning, for the back propagation learning, for SOM, that is self-organizing map, we will do in details in the next classes. So that's why I have not mentioned about this Hebb learning and all. But delta learning I have shown, because delta learning we will not cover in details in the other classes that I have shown in the diagram. So this was about the various types of the learning schemes and the network architecture. So this is about the today's session. Thank you so much. Now let me ask the questions one by one. Yes, we'll call one by one. First of all, Maharaja Surajmal. So in this session, basically we have learned about that what are the network structure, what are the learning schemes available, Hebbian learning, delta learning, perceptron learning, and in details we will say in the next sessions, and the network structures, and mainly I have focused in with the Mac-Kullak-Spit model. Mac-Kullak-Spit model, this and NOT gate and the OR gate, this all things we will do in the MATLAB programming in tomorrow's next session. In the evening session, we will do the programming, MATLAB programming of all these models or all these gates in MATLAB programming. That time it will be more clear to you. So this is all about your today's session. Now you can give me any any questions you can put.